Okay, let's read the problem. So you are given an integer. Someone is talking. Okay. You are given an integer array nums, and you have to return a new counts array. So you are given an array, and you have to return another array called counts. The counts array has the property here, where counts I is the number of smaller elements to the right of nums I. So that means we are given one array nums here, like this example, 5, 2, 6, 1, and we have to return another array of the same size, such that for each element in our output array, for each element I, it should represent the number of elements smaller than nums of I after it. So let's take this example here. So we are given here an array of 4 elements, and we have to return another array of the same size, such that for each position we have to put the number of elements greater than the elements in this position after it. So for 5, we smaller. So the number of elements smaller than this 5. So what is the number of elements smaller than 5 after it? It's 2. 1 and 2 are smaller than 5, right? So we should put here 2. And for 2, what's the number of elements smaller than 2 after it? It's only one element. And for 6, another one element, which is 1.
Are you sharing any whiteboard? We are not able to see.
You cannot. Can't you see my editor, Visual Studio Code?
Yeah, we can see your editor.
Editor, I'm able to see, but not any whiteboard.
So can you see my editor or not? Visual Studio Code. Here, I'm writing. Can't you see anything?
Yes.
Yes, it's not a whiteboard. So I'm writing here. I'll maximize the text here. So is that better? Can you see the numbers now?
Yes.
Okay.
Yes, I'm able to see.
Okay. So what I said here is that I want to put each element, I want to the output array to be in such a way that at each position it represents the number of elements greater than the element at this position, but after it. So that means so the number of elements smaller than the element in this position, not greater than. Sorry. So for 5, what is the number of elements smaller than 5 after 5? It's 2. And what's the number of elements smaller than 2 to the right of 2? It's 1 element only, which is 1. And what's the number of elements smaller than 6? They are 1. So we're counting the number of elements smaller than our current element to the right of me. Okay. And what's the count of elements smaller than 1? It's 0. There are no left elements here. Okay. So let's take another quick example here. So very quick example. So here for 5, what's the number of elements smaller than 5 to the right of me? It's 1, 2, 3. There are exactly 3 elements. And for 6, the number of elements is also 3. And for 7, the number of elements is 3. Okay. And for 1, what's the number of elements more than 1? It's 0. And for 2, we have another 0, and for 3 we have another 0, and for 9 we have another 0. Okay, so this array I didn't intend to make it 33300, but it's okay. Okay, so did you all got the problem now? So I want, if anyone have any idea on how to solve this problem, tell me. Even if it's the easy idea or brute force idea or anything. So just tell me the easiest way to solve it. Okay.
I think we can go ahead with selection sort logic.
With selection sort.
Yeah, selection sort. So moving over the right and taking the minimum, taking the count of the remaining elements which are lower than lesser than that, but it will be a brute force. The complexity will be of n square.
Okay. So I'm just going to, for every element, I'm just going to the right of it until the end and count the number of elements more than me. That's it, right?
Right. I'm thinking of another logic is I mean, not sure. One idea is, anyways, if the last element with there will be the count will be 0 because it doesn't have any numbers at the right.
Yeah.
So
Yes, right.
we can come in the reverse way so that our result will be like it's already done for the last element, right?
Yes, yes, true. So we can go from the last element, and then do you have any idea how we do it for the remaining elements? So for the last elements, it will be the last element will be 0, and for that initial brute force way, when we are going back, and if we did the same thing and counted the numbers to the right of us, it will be at the same complexity, n squared. So reverse here won't do us any favor. Okay, are you with me?
Yeah, I agree with that.
Okay, so we want to think in a way, in a faster way, to count the number of elements smaller than us. Okay, so I'll take that reverse way, and I'll solve it with this way. So it will be easier to solve it in a reverse way. Okay, so let's see how we could do it in a reverse way. So I'll say the efficient way now. So anyone I'll say it right now, but before I say it, anyone have more efficient solution before I say the efficient solution?
Hi sir, we can actually we can do from last, and so we initialize the last value as 0, and if and we go one step back, like we compare the last value. If it is greater and its value is 0, then we make it 0, and we go next to 2, and if we compare the value, if it is greater and its associated number of counts are also 0, then we make it 2. Same way
Okay,
when
but
we reach 7, so it is less. So in that case only we traverse all the other values.
okay, so that will make it faster a little bit, but again the complexity will still be of n squared, right? Do you agree with that? So
Yeah.
we could have an array such that for every
Uh,
element we traverse the whole array again.
so I have another idea.
Okay, go ahead.
So my idea would be like when we traverse on the reverse way from right to left. So we'll maintain a variable that will hold the let's say max um max smallest number or the biggest smallest number I can say.
Biggest smallest number.
Yeah, let's
Well,
say if we are for 9 it would be 0 obviously. For Okay, sorry, my thinking was wrong because we need a count right
Okay, no
here.
problem.
Okay.
Yeah, okay, no problem. Uh,
Uh,
okay, so I can make it.
uh,
Okay,
I don't know the exact one, but we can. I think we can use a stack because since there is a reference to the backward thing, we can start from the back and use some stack of caching some bigger values and removing the smaller, something like that. I guess we can use stack for this problem, but not able to figure out how to use that, whether bigger number or smaller number.
okay, so stacks are used for some kinds of problems like that, but stack will not be of benefit to us now because stack could store. So we could store what's the first element smaller than us or greater than us. So this is called monotonic stack, where we traverse from reverse to the beginning and then store for every element what's the first element smaller than us or bigger than us. We can do it that way and it will be faster. But again, we want to know the number of elements smaller than us or greater than us. So stack will not store all of that. Uh, it cannot be done, or I don't know a solution of stack that can be done that way. Okay.
Now, for
So I
example,
have
here,
hmm,
taking using a stack, will first put it in 9 over there, and it will be for 9, since no elements are there, -1. So when we see 3, we'll not put it into the stack
hmm,
because it is not greater than 9.
okay.
So the count will be what are the number of elements in the stack. So it will be 1, it will be 0 minus, means it's only one element. And if you go to 2 also, will not put the 2 inside because it is not
Okay.
greater. Then if it's 1, it is not greater than that. Okay, maybe, yeah, this may not work.
Um,
Okay.
yes, it might not work here. It won't work here. Okay. Um, so we can try to faster the brute force way a little bit. So if we are going from end to the beginning and we reached 7, for example, and we want to count the number of elements smaller than us, smaller than 7, we can go from 1 until 9 and see each element for each element if it's smaller than 7 or not. But we can fasten this with only O of log n operations. So we can count the number of elements smaller than 7 with only log n operations, given that we started from the end, not from the beginning. We cannot do it from the beginning. So how could we do that? Let's have another array here, and it is of size minimum. So another array here called A, and it's of size max element. So it's of size max element. So it should be of size 9, for example. And in our case here, since we don't know our max, we could initialize it with 10 power 4. Okay, so the size of it would be, let's make it here 9. Okay, max. So A will be initialized with all zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. 4, 5, 6, 7, 8, 9. So here our array called A, and it's all initialized with 0. And let's go from the right to the left here in our initial array and see what modifications can we do in that array to help us count the number of elements we want to count. Okay. So here, when we are at 7, if we want to know, so if I so here, if I am at 7 and I want to know the number of elements smaller than 7, I could have that array, that array I did it here, storing what are the values smaller than 7 that I passed before. Okay, so I'm passing from right to left, and if I reach 7, I will be having this array storing what are exactly the elements I have passed before. So A will be storing at 1. I'll have passed 1, one time, right? And 2, I'll have passed 2 another time, okay? And 3, I'll have passed 3 another time. And for 9, I've passed it another time. And if I add here another 2, for example, so when I reach 7 again, I'll have passed 2 another time. So when I pass on any element, I just increase the index of it in our created array by 1. So I pass 2 times, then I increase a of 2 by 2. Okay, so first I increased it by 1, then I increased by another 1. So here, when I reach 7, and I want to know what are the number of elements smaller than 7. So what I have to do here is search in this array A, is search from 1 to 6 only about the number, so the sum of elements here. Why? Because the sum of elements here from 1 to 6 represents the number of elements we passed from 1 to 6. That's it. Do you get the idea? So I didn't say now how we could make this fast in offlog but did you get the idea of how could we count the number of elements more than us? So let's before asking you, let's fill this with 0 and make it from the beginning. Okay. So what we'll do here in our algorithm that okay, we'll start here from 2, for example, from the end, right? And for 2, the first element I passed is 2, so I'll have to add 1 in our created array A, add 1 to the index 2. Okay, so it will be 1 here, and then I'll have to put the answer for 2, and it for sure will be 0 because it's the last element. And if I searched in our created array on the number of elements before 2, I found 0. Okay, then I'll put 0. Then for 9, I'll first, before updating this array, I'll first search for the number of elements before 9. So I'll search from 1 to 8 for the sum of elements here and to return 1, right? So here will be 1. And then I'll have to update this array because I visited 9. So I'll update 9 with 1. And then I go to 3. So first, I want to know the number of elements smaller than 3, which is from 1 to 2. So the sum of elements from 1 to 2 here in our array is 2. Is 1, sorry. It's 0 plus 1, which is 1. And then I'll have to update this array. So I'll update the index 3 by 1. Okay. So here are the indices for reference. 1, 2, 3, 4, 6. Okay, that way it's easier. Okay, so now here the last thing I was at 3, and I updated 3 with 1. Okay, and now I get to 2. So I want to count the sum of elements from 1 to 2 in our array, from 1 to 1 actually. So it's more than 2. So from 1 to 1, it's 0. So here the answer is 0. And then I'll have to update 2 with another 1. So I'll just have to plus 2. So plus 1 at 2. And then here at 1, I'll have to search for the number of elements more than 1, which is obviously 0. Okay. And I'll have to update 1 with 1. And then I went to 7. So I'll have to count the sum of elements from 1 to 6 in our array. So 1, 2, 3, 4, 5, 6. So the sum of elements from the index number 6 to the index number 1. So it's 4. 1 plus 2 plus 1 choose 4. Okay, and I have to update 7 with 1, right? And then 6, the sum will be again 4, and I'll have to update 6 with 1. And for 5, the sum between 1 and 4, which is again 4. Okay, so for 5, 4, and I'll have to update 5 with 1. Okay, so let's check. So we ended up with 0, 1, 1, 0, 0, 4, 4, 4. Let's check if this is true or not. So 9 is greater than 1 element, right? 3 is greater than 1 element. 2 is not greater than an element. 1 is not greater than an element. 4 is greater than 4 elements, which are 1, 2, 3, and 2. 7 is greater than 4 elements. Okay. 6 is greater than 4 elements, which are 1, 2, 3, and 2. 5, 1, 2, 3, 2. Okay. So this helper array helps us to detect the number of elements more than me. But here comes the question: how can we get the sum from some index to another index very fast? I think we said that before, so you could get it yourself before I say it. So do you have any idea? Can you say how we get the sum from index L to index R very fast? So how can we calculate sum from L to R very fast?
Prefix summary.
Prefix sum array. So keep in mind that we are updating the array. So we'll have to update every prefix. So it will take so long, right?
Yes.
Are you with me? Okay. Prefix sum array will not work because we are updating every element here. So we'll have to update every prefix array. Okay. Anyone can say we can use segment trees, right? So we said segment trees before. So with segment tree, we can get the sum from any interval. We can get the sum from left to R in O log n only, and you can update in O log n also. Okay. Do you agree with me?
Yes.
Okay. So we can make segment tree out of this array A. So we can make a segment tree, and of course it will be of size 9 times 4. And initially A will be 0, right? And when we update every element in A, so we plus any element in A plus 1, then we will update the segment tree immediately. And at each time after we update the segment tree, we'll just query we'll query about the sum of elements from some index L to some index R. That's it. Okay. So let's first, to not make things complicated,
No, but
let's make the
is it feasible?
Okay.
Because the number will be maximum, right? For example, the number can go to, I have only 5 elements and one of the number is the int maximum, like some 8-digit number. So at that time, if you get a segment tree, it will be that number into 4. Those many spaces has to be reserved. So practically, will it be possible?
I didn't quite understood you. So are you saying that if our max is very great,
Yes.
greater than 10 power 4, or
Yeah. The
if it's 10
int
power
max,
4?
so int max will be the maximum. So array should have those many elements. Because if one number is also, we are having a maximum because we need the index for that array. So the array should be declared till that maximum number, int max.
Yes.
So,
So
and if we go to the segment tree, the size will be that maximum into 4. So that will be a lot of space, right?
so you are saying that 10 power 4,
Yes.
this maximum is very big for segment tree. Okay, I got you. So here it's clear that okay, so we have the length of the array up till 10 power 5, right? And the length of the maximum, it's up till 10 power 4. Let's say it's 10 power 4 multiplied by 2, because we'll shift every positive number to every negative number to be positive. So we have a total of 2 times 10 power 4 numbers. But if we multiply that by 4, it will not pass 10 power 5. Okay, so 10 power 2 times 10 power 4 multiplied by 4 will be more than or equals 10 power 5. Okay, and 10 power 5 is actually 10 power 6 or even 10 power 7 is a very safe number for initializing arrays. It's not many. Okay, so it's clear here that we have a very small amount of elements, so it's not big at all. Okay.
Okay.
Okay. So first initialize our array A. Let's take this function here. Okay. So initialize them with fixed values, and array A will be of size. We want it to be of size maximum, right? But here is a thing. Our smallest number is negative 10 power 4, and we cannot store negatives. We don't have negative indices here, right? So we'll shift every number with 10 power 4 to the right. So that means okay, so that means if we want to update negative 10 power 4, so that will translate in our code that we want to update negative 10 power 4 plus 10 power 4, which is 0. Okay, so we'll shift every number by 10 power 4 to the right. So that means we have a total of 2 times 10 power 4 plus 1 elements, because 10 power 4 positive elements, 10 power 4 negative elements, and 0. Okay, so the size should be 2, 1, 2, 1, 2, 3, and here 2, not 1, because our maximum element will be 2 times 10 power 4 plus 1. So the size will be 2 times 10 power 4 plus 2 to access that maximum element. Okay. I have another modification here. Okay, so let's not shift every number by only 10 power 4. So let's shift it by 10 power 4 plus 1. Why? Because our elements, because to make our elements are from 1 until something like 2 times 10 power 4 plus 2. Yeah. So if we encountered negative 10 power 4, so we will want to plus it with 10 power 4 plus 1. Why we would make that? To make the starting element 1, not 0. So we want our starting element to be 1. And we'll see now why I make it 1, not 0. Because this will be easier. Because if I'm searching, if I encountered 1 here and I want to search for the number of elements more than 1, I'll just look from 0 to 0. But if our smallest element is 0, I'll have to face some corner case because I want to search for the number of elements more than 0, which are negative, and it's not good. Okay, so I'll have it started with 1. So these are small cases. It won't matter if we did like that. Okay, but I'm just, if we did it with more 5 or 6 elements, it won't matter. But I'm just saying it to be clear. Okay. Is that okay? 10 power 4 plus 10 power 4 plus 1. Okay, so that's good. And here we want to make our segment tree array. and it will be of size 2 times 10 power 4 times 4, right? So it will be nearly like, let's make it, we have enough space, so let's make it 10 power 5, okay? So it won't do us any harm here. So now we have the segment array and the A array. Let's make the functions for the segment tree, and then we make our code, okay? So first we'll have to we have two operations. We have update and we have query, which is sum. So we have update query, which we want to update any element at each position. That's it. And for sum, we want to get the sum of the elements from L to R. Okay, let's make update first. It will be void because we will not return anything. We'll just update the segment tree. Okay. So void update. So int L and int R are representing the interval we are standing at the segment tree. Okay, and int K is the index we want to update in the segment tree, and int I is the index of the node of the segment tree. Okay, so int I is the index of the node representing this interval. So L and R and I are just representing the interval. So this is the left end point of the interval, and this is the right end point, and this is the index of this interval in the segment tree. And K just represents the index we want to update. Okay, let's make I beside L and R, and here K with itself. Okay. So here we want to say that if K is out of our segment, so if K is not from this interval, so if it's more than L or greater than R, then we want to go out. So we'll not be updating anything in this interval, right? So if K is more than L or K greater than R, then just return, because it's void, so it should just go out. Right, so now we are sure that, so since this is, if this didn't happen, so we are sure that K is in our interval, right? So another case is if we are at an interval of size 1. So if we reach the last, if we are at the end of the segment tree, so if L equals to R, so if L equals to R, that means we are at a node with an interval of size 1. That's it. So that means we are standing at K. We are standing at a node representing an interval of size 1, and K is in this interval. So that means we are standing at K exactly, right? So just want to update the segment tree. So segment of I will be equals to, so remember, K representing the index in our initial array that we want to update, okay? So the node will be updated with the value of A of K, okay? And at last, if we are in the interval, but we are not of size 1, so we will have to update the two smaller intervals to the right of us and to the left of us, and then go until we reach this state. So just recursively, we'll do else. We'll recursively update the two smaller nodes. So let's have here middle equals L plus R over 2. So we'll update from left to middle, and I multiplied by 2 plus 1. And K will be as it is at every call. We won't change anything at K, okay? So we'll update the left, and we'll update the right. So from middle plus 1 to right, I times 2 plus 2. Okay. So here I updated the left and right, and they will eventually, until they reach an interval of size 1, they will keep updating until they reach this. and segment of I will be changed to A of k. So I know that after updating the left and right, I should have some changed values in the segment of I. Okay. So after updating the left and right, I should update the segment of I will be equals to sig of 1 multiplied by 2 plus 1 plus. So why plus? Because remember, in segment tree, in this segment tree, we want to get the sum of some interval. So at each segment LR, so segment LR represents the sum of all elements from L to R. So here I'm updating the segment from L to R. I'm updating the value of it to be the value of the sum of the segments from L to mid plus the segments from middle plus 1 to right. Okay. So now I finished the update function. Um, anything not clear about the update function here? If you have any question in any line of code, just ask. Okay. So let's go to the sum function. So the sum function should be integer because we want to return the sum between L and R. So now we'll have to pass many parameters. So be int L, int R, representing the interval of the segment tree we are currently standing at. Okay. And int I representing the index of the node in the segment tree. Then we want to have another L and another R, capital L, capital R, representing the interval that we want to get the sum of. So now the first L and R representing the interval we are standing at the segment tree, and LR representing the interval we are searching about its sum. Okay, so that's it, it's 5 parameters. Now we'll have 3 cases. The first case is if the interval we are looking at its sum is out of the interval we are standing at, then we will return 0. So if these two intervals doesn't intersect, so we'll just return 0 because we don't want anything from this interval. So to check if they doesn't intersect, we'll say if R is smaller than L or L is greater than R. So if the right endpoint is more than the left endpoint, or the left endpoint is greater than the right endpoint, then it's clear we are not intersecting, then we'll return 0. Okay, so after that, if it didn't reach this, so we know that we intersect with the interval. So the other case is if this interval we are searching for is completely, or no, the opposite. If this interval of the segment tree is completely in our interval we are searching for, then we will return the value of this node in segment tree, right? So if this interval is completely in our interval we are searching for, we'll just return segment of I. So if L greater than or equals L and R smaller than or equals to R, then we'll just return segment of I. So the last case is, so if we are intersecting and it's not completely inside, then I know that they are intersecting in some way, and we want to go furthermore to the left part of the segment, to the left child and to the right child of the segment tree. So we'll just return sum of the left point of the left part plus sum of the right part. Okay, so int middle equals L plus R over 2. So sum L mid I plus 2 plus 1. And again, L and R will be the same on all the calls because this is the interval we're searching for. So we'll return this plus sum input plus 1, right, if2 plus 2, LR. So here our sum function is complete. So now here, this should return the sum of any interval from L to R. So any questions in these two functions? Someone wanted to ask, I think. Okay, so no questions in these two functions before I continue? Any questions at all? Okay, let's continue with our program. So now we have nums array. So what do we want to do here? So we want to go from the right to left and then update A accordingly, right? So let's see. So we'll loop from the last element of nums. Let's make first n equals nums dot size. So now I know that nums, the elements of nums are from negative 10 power 4 to 10 power 4. So before I touch any element, I want to increase it by 10 power 4 plus 1. So it's 1e4 plus 1. No, what's up? So nums of I plus equals 1e4 plus 1. Okay. So now before I touch any element, I just increased its value to access A as I want. So now I want to, so before I update A with this value, I want to get the sum first. So I want to get the sum of the elements smaller than me. So I want to have vector here storing the answer that I will return this array. So vector int answer. Okay, and it should be of size n. So answer of I should be equals to the summation of the values from 1 to, or actually from 0 to nums of I minus 1, right? So we'll call some. So for the segment tree, we want to start from the very big node, from the first node, which should be from 0 to 2 times 10 power 4 plus 1. 1, 2, 3, 4. Okay. And I is from 0. And our interval should be from 1 to... yes, any question? Something happened here. Are you disconnected or with me? Do you all hear me?
Yes, but we are not able to see the screen.
Okay, so I think it was disconnected for a second. So what's the last thing you were with me? I wasn't concentrating. So what's the last thing you heard? Oh, you are not seeing the screen now? Okay.
No, not we are not seeing the screen.
Okay, I'll share it now. Can you see it now?
Yeah.
Okay, so what's the last thing
Yes,
you...
summation 35 line number you're telling, like, I mean, from sum.
Okay. So now I calculate the sum. Let's say this line again. So for answer of I stored in the answer, which is the sum, and I look at the segment tree, but the sum from the interval from 0 to nums of I minus 1. So if nums of I is 7, so I look for the sum from 0 to 6. Okay, and of course the parameters here for the segment tree, I'll start from the very first node, which is of index 0, and which is the biggest interval possible in the segment tree, from 0 to 2 times 10 power 4 plus 1. Okay. So I have now to update the segment tree with this value nums I. So I'll first update the A array. So A of nums of I plus plus. So that means I passed on nums I. And then I'll just call the update in the segment. Again, I'll start from the first node, 0. And for k, it will be nums I. So I want to update A at the index of nums I. Okay. So there are many indices here, so I know you might be confused here. But okay, if you want any question, ask. So I calculated the sum and I updated and then updated the segment tree. Then at the end, I should have answer ready with our answers. So I'll just return answer. Okay. I think this should work. Let me take a look if there is any bug here. Okay. So while I'm looking here at the code, ask me if you have any question in the code. Okay.
Just I have a doubt at the line number 15. So it is how you are calculating till half of the like update is there, right?
Yes.
Third
I'm updating.
parameter from L to mid, and this I, the third parameter in that I into 2 plus 1, like till how long it will be, till only mid, right? I didn't get, because I'm not good at like CPP.
Okay, so do you know segment tree, right? Or
Yes.
okay, so here you are asking about this I times 2 plus 1 or
How?
about mid?
Yes.
Okay, so I times 2 plus 1 is just the index of my left child, because we said here that for the segment tree, so the first node is 0, and my left child is 1, and my right child is 2, and the left child of 1 is 3, and here another 4, and here 5, and here 6. So what I'm saying here is that if I want to access my left child at any point, it should be of index I times 2 plus 1. Why? Because it's a sequence here. So 0 times 2 plus 1, 1. So now I'm accessing my left child. And 1 times 2 plus 1 is 3. So now I accessed my left child.
Okay. Okay.
It's just the index, okay? And I times 2 plus 2 is the right child. That's it. Okay, let's test it. Okay, so everything's good. So let's submit. Well, I'm not sure if there are small bugs or not, but let's try and submit. Let's actually try our example here. I should print 011000444. Okay, that's right. That's right. Okay, accepted. I'll send you the solution here in the chat. Paste them. So here I sent you the solution in the chat. Let's go to the next problem. Okay, let's see this problem. I sent the problem link in the chat. Have a look at it and take 3 minutes to read it and discuss it. Okay.